Hello, and welcome to the module on work and energy. This is really an exciting moment in physics because we're about to learn about energy and energy conservation, and we'll be using those ideas the rest of the semester and next semester too. So we'll start at the beginning. Work is not, in terms of a physics definition, isn't exactly like your common usage definition. You might say, oh, I worked really hard. I sat at my desk and I worked 3 physics problems. That's a different kind of work. This is a physics definition of work. And it is when we have a force applied over a distance. So I can calculate the work done to, say, take this box from where I have it marked in black to where it is over here dashed. Let's suppose I wanted to attach a rope to it and pull the box across the floor some distance d, and I used some force F. The work that I did is the force times the distance times the cosine of the angle between them, where I could write this as so that is a vector. I could write this as a displacement vector, or we could call it x or d. We've been calling displacement x most of the time. But this is just a switch to using d in terms of the notation. And definitely these are vector quantities, but into this equation, they just go as scalars. So it's just the magnitude and the units and the angle there. That gives us the work that's been done. Now we're going to talk about our 2 introductory kinds of energy: kinetic energy and potential energy. We're starting there. But as I said earlier, we're gonna add on other kinds of energy. We'll talk about electrical energy in physics too. So we're gonna add on other kinds of energy later. We're just starting with kinetic and potential because they involve ideas that we've already been studying this semester. So kinetic energy is energy due to motion. Anything that has mass that's moving has kinetic energy, and this is how we calculate it: 1/2 mass times velocity squared. We can calculate the kinetic energy of a cannonball using that. We can calculate the kinetic energy of an electron using that. So it's always going to be 1/2 mass velocity squared. Word about notation. So our book uses KE. That's what you're going to see me using, but I know that a lot of you learn with other resources, so I just want to note that you might encounter, if you're using other videos or other books, just K, and you also might encounter just T for kinetic energy. I'm going to come back to this picture in a moment. First, I'm going to introduce potential energy. So again, notation, we're going to use PE, but you might, if you're using other resources, see capital letter U used for potential energy. And if you like those resources, go ahead and use them. Just know it's different notation. Potential energy is energy due to position. And while kinetic energy was always going to be 1/2 mv squared, potential energy is going to depend. So one way that we can have energy due to position is if something has position in the gravitational field. So I'm holding a marker right here, and it is some height above the floor. And so it has the potential to fall. If I let go of it, it's gonna fall. And as I let go of it, it was at rest. It had a no velocity, and it had the entire height to the floor with which to fall. And as it fell, we know from prior chapters, it went faster and faster, right? It started off with 0 velocity, And by the time it got to the bottom, almost to the floor, but right before impact, it had its maximum speed. So if I want to think about a projectile that goes, maybe I shoot it with a t-shirt cannon or something like that, up and it comes down. At the bottom here, if I put my origin right here, my kinetic energy is 1/2 mass velocity squared, and that's the speed with which I shot it. It's gonna go up, 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 up to some height h, and at this top spot, what do we remember about the speed up there? Its speed in the y direction is going to be 0. So it will, if we consider just the y direction here, so maybe instead of that drawing, a drawing more like that, just to simplify this a little bit, put it in 1D. It has kinetic energy is a max down here, and potential energy is 0 down here. Up here, the kinetic energy is 0 just for an instant when the velocity is 0, and the potential energy is a max at the top. All right, so that's our first kind of potential energy. Is it due to position in a gravitational field, and the way we're going to calculate that is mass times the magnitude of gravity, don't put a negative sign in there, times h. That's the height. And so this really depends on picking an origin. That's going to be an early step in most of these problems. The second type of potential energy we will look at is potential energy in a spring, and we calculate that using 1/2 kx squared, where x is how far the spring has been either stretched or compressed from equilibrium. And the k is the exact same k that we used in Hooke's law from a previous chapter. All right, we've got a couple more. The work kinetic energy theorem says that the net work has to equal the change in kinetic energy. So let's suppose I had a bowling ball rolling towards me and it had some initial speed, and I wanted to slowly apply a force over a distance to slow it down. It would have and maybe I'm going to slow it down until it stops. So in that situation, I would have I'm going to have kinetic energy final minus kinetic energy initial. In that situation, that's 0. So my work done is going to be negative whatever my initial kinetic energy was. On the other hand, if I have a bowling ball that's at rest and I apply a force to it over a distance, my initial is 0. And so now my work net is going to be positive, and it's going to be positive whatever my final kinetic energy is. The units on work are the same as the units on kinetic energy, are the same as the units on potential energy, and they are joules, which are the same as a kilogram meter squared per second squared, or a Newton times a meter. I'm going to head back over to our last equation. We are introduced to power in this chapter. Power is another one that we're going to be using for the rest of physics. It is defined initially as work divided by time. We're going to see that since work can be calculated different ways, I could get work as the change in kinetic energy, so power could also be change in energy divided by time. Next, we're going to look at energy conservation in two different classical systems. All right, so now using those definitions that we've just been introduced to for kinetic energy and potential energy, we're going to talk about energy conservation. The total energy initial has to equal the total energy final if energy is conserved. If energy is conserved. So all of the kinetic plus all of the potential initial has to equal all of the kinetic plus all of the potential final, provided energy is conserved. If it's not conserved, then what I can just do is tack on there how much work was lost. And this still should be an equation that's valid. I like to imagine energy conservation as if I had two glasses. Glass we could consider labeled kinetic energy and one labeled potential energy. And let's suppose the example that I used earlier of if we just shot a projectile straight up and straight down. I would have no potential energy at the beginning. So let's say this glass potential energy is empty and it's all kinetic. So this glass with kinetic energy represented is full. And as the projectile is shot up, the water gets poured from the kinetic energy glass to the potential energy glass. When the projectile is at the very top, we have no kinetic, all potential. And then on the way back down, we pour it back into the kinetic energy glass again. If I don't spill any water, at any given moment, I could freeze, stop, and I would have maybe some water in each glass. It's just at the beginning, I had all in one, at the end, I had all in the other. But any spot along the way, I can always add them up, and the initial total should be equal to the final total. In the case of work loss, we're going to have work loss sometimes due to non-conservative forces. In this course, the only non-conservative force that we're going to be dealing with is friction. And the way you can kind of relate that to this analogy of two glasses of water is I'm still pouring the water from one glass to the other, but as I do it, I'm spilling. I'm spilling on the floor or the table. But if you take my initial amount of water or energy, set that equal to the total at the end, and then add the stuff that got spilled, this should still be a valid equation. So we're going to solve problems using energy conservation, and sometimes we won't have any work that's lost, in which case that term is zero. Now I've written the most simple version that we can here, one kinetic and one potential. One kinetic and one potential. You will encounter situations where you have more than one potential. You could have gravity and a spring at play. You could have more than one object. And so then you might have, if the two objects are moving, you would have two kinetic energy terms. So but we'll look at those problems in detail later. The first system I wanted to show you here is a pendulum system. So I have a pendulum, and notice I'm picking to put my origin at the bottom of the pendulum swing. I could really put my origin anywhere, and as long as I pick an origin, don't move it during the problem, and all of my numbers, like for position, come from comparison to that origin, I should get the same answer no matter what. But let's suppose I'm gonna have that be my final and this be my initial. And I'm going to take this stretched pendulum, and you can see I have non-conservative forces present here. I am losing energy in this system because ideally what would happen is this would start here, come through there, come up here, come back, right? And it would just keep going. So let's kind of figure, we might want to think about a problem where this is the initial and this is the final. Would it keep moving? Sure would. But if we're just want to like freeze frame on this as the initial and this is the final. And again, I have kind of some assumptions that aren't always true. Let's suppose that here the velocity is 0, which just means I'm going to release it. I'm just going to let it go. So it has an initial velocity of 0, which would mean its initial kinetic energy is 0. Since I put my origin here, it has an initial height. So it would have an initial height that we could calculate if it wasn't given. And my final spot here, it's going to be zipping through that spot. It's going to have its maximum speed at the bottom of the pendulum. And what's the height at my final location? Well, I put the origin there, so the height's 0. So because the potential energy is 0, that means this has to be a maximum. So that's a pendulum system. Keep in mind that my example I just gave here had this as an initial velocity of 0, and that we won't always just have it released. We could throw the ball. Now, let's think about a mass on a spring system. And I'm going to pull the mass down and release it, and we'll watch the energy get converted back and forth between kinetic and potential as this bounces up and down. All right, since I put my origin here at equilibrium, let's suppose I'm going to take this as my initial and this as my final. So if I decide this is initial and this is final, that means the final height is 0.
I've sketched both the initial and the final moments of this system and written the energy conservation equation for the initial and the final beneath them. Notice that there is kinetic energy and both kinds of potential energy, that due to gravitation and that due to a spring, in this system. Let's think about the initial height. Because I put my origin above the initial location, my initial height will be negative. My final location is right at the origin, so my height final will be 0. My initial speed will be 0 because I'm just releasing the mass at that location. My final speed will be the maximum speed that the bob ever has. Now let's think about the delta X term in the potential energy due to a spring system. That delta X is how far the spring has been displaced from equilibrium. Since I placed my origin at equilibrium, delta X initial is just going to be the same as HI. The final location has the spring at equilibrium, so delta X will be 0. Now, just not writing all of the terms that are 0 in this, I can write the energy conservation equation for this system.
Great, and those are our first 2 introductory energy conservation examples.